determine if the voltage drop calculation is correct, let's review the steps and formulas used. The situation involves a 50 amps, 240 volts circuit running to 2 poles. The distance from the panel to pole number 1 is 125 feet, and from pole number 1 to pole number 2 is 260 feet. Each pole has 4 1000 watts metal halide high-intensity discharge lights, which are contactor controlled. Each ballast draws 4.5 amps. The voltage drop formula used is voltage drop equals 2 times K times length times current divided by circular mils, where K equals 12.9 for copper. Firstly, let's review the voltage drop calculation from the panel to pole number 1. The formula is voltage drop equals 2 times 12.9 times 125 feet times 36 amps divided by 16,510 circular mils for number 8THHN wire. This results in a voltage drop of 7.3 volts. Secondly, this is under 3% of 240 volts, so it seems acceptable. Thirdly, the voltage drop calculation from pole number 1 to pole number 2 is voltage drop equals 2 times 12.9 times 260 feet times 18 amps divided by 26,240 circular mils for number 6THHN wire. This results in a voltage drop of 4.6 volts. It is correct to consider the two separate sections of the circuit and calculate the voltage drop for each section separately. Now let's analyze the calculations. For section 1, from the panel to pole number 1, the distance is 125 feet, the current is 36 amps, the conductor is number 8THHN, and the calculated voltage drop is 7.3 volts. For section 2, from pole number 1 to pole number 2, the distance is 260 feet, the current is 18 amps, which is 4 lights times 4.5 amps each. The conductor is number 6THHN, and the calculated voltage drop is 4.6 volts. To find the total voltage drop, sum the voltage drops in each section. Total voltage drop equals voltage drop 1 plus voltage drop 2, which is 7.3 volts plus 4.6 volts. Resulting in a total voltage drop of 11.63 volts. Now let's calculate the percentage of voltage drop. The percentage of voltage drop is calculated as total voltage drop divided by supply voltage times 100%. Percentage voltage drop equals 11.63 volts divided by 240 volts times 100%, which equals 4.85%. The calculated voltage drop of 11.63 volts results in a voltage drop percentage of 4.85%, which is slightly higher than the initially assumed 3%. Now for a note. It is important to consider the inductive nature of the lighting loads when calculating voltage drop. Inductive loads can cause additional voltage drop, which is not accounted for in the calculations. If the lighting loads are significant, it may be necessary to use a larger conductor size or install a power factor correction capacitor to reduce the inductive effects.